So hello everybody, my name is Vana Jelicic. I'm a PhD student in electronics from University of Zagreb, Croatia. And today I will present shortly something about holistic approach to energy saving in wireless gas sensor networks. So I come from Faculty of Electrical Engineering and Computing from Zagreb, and I work on a project that's called Across. You can find more on this slide, but basically it's an FP7 regional potential project that combines research from cognitive and robotic systems, network embedded systems, control methods, and renewable energy systems. And there are quite a lot of research groups from our faculty taking part in this project. And the group that I'm taking part of is called Advanced Instrumentation Group. We are very much application oriented. Our expertise are in sensors and sensor interfaces, especially hardware design and measurements. We work with embedded systems, microcontrollers, FPGAs, and we do research also in wireless sensor networks, especially in terms of power management and signal processing. We have some experience in environmental monitoring applications. A couple of years ago we had a project of designing and deploying wireless sensor networks in olive orchards. We have a project of monitoring asthma, especially in detecting bees on patients and also in monitoring air quality. And we had some smaller projects in bird monitoring in marinas and also fall detection. So the research that I'm doing for my PhD is about power management in wireless sensor networks with energy-hungry sensors. And I'm focused on system level, so I study the system as a whole. And most research I've done was in collaboration with the University of Bologna, where I spent about a year and a half in the last couple of years as a visiting researcher. So we heard here in the last couple of days, we mentioned TLOS B modes, iSense modes, other modes. So a typical wireless sensor node has a sensing unit, a processing unit, communication unit, and a power unit. Power unit means battery or some harvesting circuitry. And the main requirements for a wireless sensor node and network is autonomy and long lifetime. That means that energy efficiency is a very important issue. So classical wireless sensor networks that started like 20 years ago were focused on simple wireless sensor nodes that measured like temperature, humidity, and those sensors consume not as much energy. The most energy consumed on those wireless sensor nodes was by radio. So we have here an example of a Texas Instruments CC2420 radio that is nowadays the most popular low power radio. It consumes about 70 milliwatts, and one of the sensors for the temperature and humidity, SHT75, consumes 3 milliwatts when active. So we can see here that radio consumes much more energy. But what if we want to use wireless sensor networks with energy-hungry sensors, which means that the sensors consume as much as energy or even more than the radio? For example, a gas sensor, here for E2E, most technology consumes about 70 to 100 milliwatts. That means that in that case we have to combine power management on the sensing unit and the communication unit, which by now was studied separately. So the objectives of my work is to prolong systems' lifetime and also to maintain good quality of service. High-consuming sensors or energy-hungry sensors are the sensors that give more complex, more sophisticated information about the environment. It can be gas sensors, CMOS cameras, snow-level sensors, and they usually monitor events that are rare. So hopefully gas leakage doesn't occur that often in the environment. So how to reduce the activity of the sensor? We can use fixed duty cycle, but then it can occur that we have energy wasting because the sampling frequency is much higher than the frequency of change of the phenomenon that we monitor. We can also have adaptive duty cycle, which means that we sample more frequently where something interesting occurs. And we can also have event-driven sensing, which means that we add to the area some low power sensors that give a rough idea of the events in that area, and when they detect some interesting event, they turn on the high consuming sensor. In that case, we have multimodal and hierarchical networks. So that was about reducing activity of the sensors. When we talk about reducing activity of the radio, in the last 20 years, there's been a lot of literature about that. The most common way is to use duty cycling, which means we turn the radio on and off periodically. In order to reduce the energy consumption, we want to reduce duty cycling as much as possible, which means we want to have the active time as low as possible and the period as long as possible. But we have to take into account when doing that there is the danger of delay, which means that unfortunately when the radio is off, it can't receive any message. So if the message arrives when the radio is off, we have a lot of delay. So if it arrives just when the radio is turned off, we have maximal reaction time. There have been many MAC protocols developed for various sensor networks, SMAC, BMAC, XMAC, I won't go into details, but their main goal is to optimize delay versus energy trade-off. And in the last couple of years, a hot topic in research is wake-up receivers. So the idea is to add to the main radio some ultra-low power continuously monitoring circuitry that listen to the channel all the time, and if they detect a wake-up signal of the sensor node, they turn on the main transceiver and they exchange the data, the main transceivers. So the benefit is that there is no idle listening of the main transceiver, and there is no energy versus latency trade-off. But there are some other trade-offs in that technology, like wake-up range versus energy consumption, wake-up range versus delay, or whether to use in-band or out-of-band radio. So there is still no practical application of these wake-up receivers, and there are also very few examples commercially available. So the challenge in gas wireless sensor networks that I've been facing are to reduce sensing energy consumption by using hierarchical sensing and context awareness, and to reduce radio energy consumption by using duty cycling or also wake-up receivers. And the main goal would be to detect events, so detect high gas concentration, detect leakage, and also to reduce latency. We want to trigger alarms immediately, or we want to turn on the ventilation as soon as possible. So we are working with gas sensors that are metal oxide semiconductors, MOX technology. They are quite small, and their principle of work is that they have a sensitive layer, and that layer has to be heated in order to enable the chemical reaction to occur between the sensing layer and the polluted particles from the air. The change of resistance shows us the concentration of the pollutant in the air. Unfortunately, we see that it takes quite a long time in terms of wireless sensor network, long time to reach stable state for that sensors, which means like a couple of tenths of seconds, which is quite a long time if you want to reduce energy consumption. So we want to reduce the activity of gas sensors, and we decided for indoor applications we want to use people presence, and we want to modify sampling frequency of the sensors based on the information of how many people are in the room. So for example, during the night, we want to sample, let's say, once per hour, and during the working hours, we want to do it more often because of safety reasons. So low power sensors that detect people presence are pyroelectric infrared sensors. They are often used in alarm systems as digital sensors, so they give like binary information, person, no person in the area. But they also have analog output because actually there are two sensing elements connected differentially. So from the output we can also recognize which direction the person is going. If it goes in one direction, the first peak is positive. If it goes in another direction, the first peak is negative. And also there are some publications that say if we combine peer sensors in an array, they can give information about distance of the person or number of people in the area. So the approach that we propose is to use different sensing modalities in various gas sensor networks connected in hierarchical manner using gas sensors and peer sensors. And we want to have event-driven sensing and communication in the network by using wake-up receivers. So the power management will be performed on the sensor level, on the node level, and on the network level. Some preliminary studies and results were already published in those two papers, so you can have more information if you contact me. These are the titles of the papers. The basic idea is to reduce energy consumption on 3 levels: on the sensor level by duty cycling the gas sensors, and by early detection of safe conditions, which I'll explain a bit later. Then on the node level, we use some sensor nodes with very low sleep current, and we duty cycle the whole node. And we modify the duty cycle based on information of people presence. On the network level, we modified the duty cycle based on information from the neighboring nodes about their state of alarm or no alarm. So, early detection of safe conditions. Here you can see 3 outputs of MOX gas sensor. First, the red one is the gas sensor in clean air after a long inactive time. So it means that the sensor was off for a long time, we turn it on, we see dropout, and it slowly goes up to some stable state. So this here happens because during the inactive time, a lot of dust and other particles from the air, they are stuck on the sensitive layer, and when we turn on the heater, those particles have to burn out. And slowly we get to the stable state, and then the resistance tells us about the state of the pollutants in the air. Here on the green curve we have clean air after short inactive time. And here we see the resistance doesn't drop that much, and it goes to stable state much sooner. And of course, since the same conditions there are in the air, the resistance value is the same. And in contaminated air, after short inactive time, the blue curve, we see also that there is not much dropping down in the resistance, and stable state resistance is lower, which means that the air is contaminated. So what we want to do, we don't want to wait here for 10 seconds. We want to find out how to make some conclusions about the pollution in the air by figuring out from this transient state what can we conclude. So let's say we know that we turn on the gas sensor a short time, so we don't have this long inactive time. Then we can suppose that we have some threshold, and we can say just after 50 milliseconds here. If the resistance is above this threshold, it means that the air is clean, so we don't have to keep on heating to find out what the exact concentration is. And if the resistance is below the threshold, then we want to continue heating and to see in stable state what is the state of the contamination. These are preliminary results. We have to do some more tests in a controlled environment, but we think that there could be some interesting stuff to discover just from the transient state. So to sum up, to date we have proposed some energy saving policies in various sensor networks for gas monitoring using peer nodes in multimodal networks and with adaptive duty cycling. And since we want to use various wake-up receiver solutions, we did some extensive study and comparison of to-date present solution in literature. Ongoing work, we are designing our solution of wake-up receiver to be used in gas sensor network, and we want to do analysis of energy consumption versus delay. The final goal is to propose a multi-level approach to enhance energy saving in wireless gas sensor network, and we also have a real-world application since we have built already a wireless sensor node with gas sensors, of course from off-the-shelf components. So shortly that would be it. If you have questions, please.
One very short question. Why you choose wake-up receiver oriented protocols?
Because we think that in terms of energy consumption and delay, it is the best solution. For that case of monitoring rare events.
Rare events?
Yes.
And can you give a bit more details on what wake-up radio you use here in the implementation?
Okay, so commercially available, there's something from Austria Microsystems. It is low frequency chip, 125 kilohertz. So one idea would be to...
It's an out-of-band solution.
Sorry?
Out-of-band solution.
No, if you modulate, so if you have, I don't know, Zigbee, something like that, for the wake-up signal, you just, it's on-off protocol. So you just give some short sequence on-off and you filter it out before the real chip. That's the only commercially available solution. And we are working with some RF design guys that are working on designing by themselves from off-the-shelf components their own receiving channel. So without using actual chip already commercial. It should be a rectifier that basically filters the received wake-up sequence.
Any more questions?